Okay guys, so this is the last case for the Euler's equation. We're going to deal with repeated roots this time. So this is our differential equation. The first thing that we want to do again is to check and make sure that it is in fact an Euler's equation. The way that we do that is we recognize that we have a t squared in front of the y double prime, we have a t in front of the y prime, and a constant in front of the y. So yes, it is an Euler's equation, which means that we can assume the form y is equal to t to the r, where we are solving for our roots r. So let's go straight into the characteristic equation. We have r times r minus 1 plus 5 times r plus 4 equals 0. Now let's go ahead and multiply that out. So r squared minus an r plus 5r, so plus 4r plus 4 is equal to 0. So this factors to r plus 2 times r plus 2. So we have repeated roots, -2 and -2, which means that we only have one solution, y1, which is equal to t to the -2. And because we only have one solution, we have to do something to get another solution. And that process is called reduction of order, which I introduced to you guys in the repeated roots case for the constant coefficient equations a few videos ago. So the way that we do that is we assume a form for our y2 as some unknown function v of t times our y1. And in this case, it is v times t to the -2. So this is the form that we are going to assume. Let's go ahead and differentiate it twice and throw it back into our differential equation. So y2 prime is equal to v prime t to the negative squared. Gotta do the product rule. Minus 2vt to the negative cubed. And then let's go ahead and get our y2 double prime. So we get v double prime t to the -2 minus 2v prime t to the negative cubed minus 2v prime t to the negative cubed, and then plus 6vt to the -4th. So we have our expressions for y2, y2 prime, and y2 double prime. So let's go ahead and throw it back up in our differential equation. So we got t squared times y2 double prime, which is v double prime t to the -2 minus 4v prime t to the negative cubed, and then plus 6vt to the -4th. All right, so let's add in the 5 times t times y prime, or y2 prime, which is v prime t to the -squared minus 2vt -3, and then finally plus our 4 times y2, which is just this. And all that has to equal 0 because we are homogeneous. Okay, so let's go ahead and distribute the t squared 5t. So we get v double prime minus, let's see, that should be a cubed right there. It looked kind of weird. But anyway, minus 4v prime t to the -1 plus 6v t to the -squared. And then plus 5v prime t to the -1 minus 10v t to the -squared, and then plus 4vt -squared. Okay, so let's see what cancels. Okay, so we have a v double prime all by itself. Then we have a minus 4v prime t to the -1 plus 5v prime t to the -1. So that gives us a plus v prime t to the -1. And then, let's see, we have a plus 6vt to the -squared, and then minus 10, so we're at minus 4, and then plus 4. So all these cancel out. All right. Okay, so this is the differential equation for v that we need to solve in order to find v and then get our y2. Okay, so what I'm going to do is I'm going to reduce the order of this guy. I'm going to say, all right, let w equal v prime. So that means that w prime is equal to v double prime. So let's go ahead and rewrite this in terms of a first order equation. So we have w prime plus wt to the -1 is equal to 0. And I'm going to rewrite this as dw dt is equal to -w over t. The only reason why I'm writing it like that is because this is separable, and I like looking at it like this. So anyway, dw over w is equal to -1 over t times dt. Okay, so let's integrate both sides. So this integral gives us natural log of w, and this integral gives us the negative natural log of t. And I'm not going to worry about keeping up with the constant because that's just going to come in at the end. So anyway, I'm going to rewrite this as ln of t to the -1. I'm going to take advantage of the properties of logarithms so that I can e both of these sides, and I get w is equal to t to the -1. But remember that we made a little substitution back here, so let's take this guy. W is equal to t to the -1, but w is also equal to v prime, so t to the -1 is equal to v prime. So all we have to do is just integrate both of these sides, and we get v is equal to the natural log of t. And again, I'm not worrying about keeping up with the constants that come into play because that's just going to be tacked on at the end. There's no point of keeping up with them. So anyway, yeah, we just integrated both of the sides, and we got v is equal to natural log of t. So now that I have my v, that means I have my y2, because y2 is equal to v of t times y1, which is equal to v times t to the -2. So in other words, my y2 is equal to the natural log of t times t to the -2. Okay, so we have our y1, which we said was t to the -2, and now we have our y2, which is the natural log of t times t to the -2. So our final solution we just express as linear combinations of our two solutions, and again, this is why I didn't bother keeping up with those constants of integration before. So our final answer is c1 times t to the -2 plus c2 times the natural log of t times t -2. This is our answer. And the cool thing to know is that no matter what, in an Euler's equation, for the repeated roots case, our v is always going to be natural log of t. Just like in the constant coefficient case, where I said our v will always come out to be t, that's the same thing for Euler's equation except for its natural log of t. So that's a little shortcut. You don't have to go through that reduction of order every time because it's going to be the same thing every time. So anyway, thanks for watching, and I will see you guys later.